Welcome back, Physics 40B, to another explainer video. This is explainer video 19.59, and holy crap, is this one bad. I hate this problem. Anyway, so let's get into it. This basically covers week 6 and week 7. It's a combination of both. We're going to use both the ideal gas law and we're going to use the law of thermodynamics, which is pretty exciting, so let's get right into it. Anyway, so this is 19.59. Just in case you're doing the wrong video, hop out. Alright, let's do it. So 19.59. Here's the question. So you come in one day and you find a well-insulated 2,000 milliliter thermos bottle containing 500 milliliters of boiling liquid nitrogen. So this implies that there's 500 milliliters of liquid nitrogen and the rest of it, the 1,500 milliliters, is gas nitrogen. So it's sitting there at 1 atmosphere and it's in equilibrium. And then for some reason you decide to take a piece of iron that weighs 197 grams. That's at room temperature, and you just throw it in there and you seal the cap, and then you wait for it to reach the new thermal equilibrium. So it's asking us, what is the pressure inside the thermos? And it's giving us the density of liquid nitrogen, which we'll use later. So basically, we got to calculate the amount of liquid nitrogen that gets converted into gas nitrogen, and then calculate the pressure from that. So let's get right into it. So we need to find the heat transfer. So we know that the nitrogen boiling point is 77.36 Kelvin. I looked it up. And then we know the equation for heat energy transferred because we looked it up. And then we also know the specific heat of iron because I looked it up. There's a theme here. We're going to look up a lot of things. So we're going to use that equation. We have the specific heat of iron in grams per, or joules per gram. And then we have the mass of the iron, which is in grams as well. And we have the change in temperature. So room temperature is about 296 Kelvin. I looked it up, and that's what it said. So that's what we're going to use. You're going to subtract that by the boiling point of the boiling temperature of nitrogen. So we get 218.64 Kelvin. We're going to plug that into the equation, and we get the change in heat, or like the heat transfer, is 19,382.436 joules. Nice. So we're basically going to use that value of joules, that energy, and then figure out how much of that liquid nitrogen gets converted into a gas. We use that by using the latent heat. So we looked that up. The latent heat of nitrogen is 199 kilojoules per kilogram. Cool. And then we also know the equation to find latent heat. It was supposed to be there, but it started there. E equals ml. So E is basically the energy, mass, and then the latent heat capacity. So here we go. Let's just plug it in. So like I said, we know the latent heat capacity. We're going to convert the 199 to kilojoules to joules. So we're just going to multiply by 1,000. And then we're going to plug it straight into that equation. So we know that the Q, we calculated that in the last slide, plug that in straight there, and then we plug in L, and then we get the mass is equal to 0.0974 kilograms. Great. And we're going to take that mass, we're going to find the molar mass. So we need to know the molar mass of liquid nitrogen, which is 28.014 grams per mole. And we can use this triangle that we learned in high school to find out moles. So if we want moles down here, we need to put the mass over the molar mass. So that's what we have right here. Moles equals mass over molar mass. So we have mass we calculated in the last slide. We just plug it into mass, and then the molar mass we just calculated. We looked it up. It's right here. This is in grams. So we're going to convert that to kilograms. That's why it's 0.028. You just divide by 1,000, and then we get that we have 3.48 moles. So this is how many moles of liquid nitrogen gas got converted of liquid nitrogen got converted into gas. Cool. So now we find the volume of the original liquid liquid nitrogen. So we use the V equals mass over density. So we know the mass is 0.974 kilograms, and we know the density is 808 kilograms per meter cubed. They gave us this in the beginning of the thing, but I forgot to use it, the 810, so I looked it up, which is kind of clumsy of me. But whatever, we're just going to use the 808 because that's what Google says, and Google's always right. So we plug that straight into our volume equation, and we get 1.205 times 10 to the negative fourth meters cubed. Oh my god, this problem sucks. Great, so now we have the volume. Now we have to find the original mass of the gas nitrogen. So we had the original 1,500 milliliters of gas nitrogen. We got to find the mass of that, okay? So we're going to use the ideal gas law, right? So and by mass, we mean like molar mass, right? So the N in the ideal gas law stands for molar mass. So we're just going to isolate that. We get PV over RT. And then V, we use the VV before the heat transfer, which is the 1500 milliliters. You convert that to meters cubed. And then the temperature is 77 Kelvin. The pressure is 1 atmosphere, and that's just 1 atmosphere in pascals. And then R is the ideal gas constant. So we just plug that straight into the equation, and we get that the moles is 0.238. Great. So here we go. Last step. We're going to add the moles and the volumes that we calculated before, put them together, and then we're going to use the ideal gas law again to calculate for pressure. So the total moles, so the original moles that were already a gas and then the ones that got converted is 3.718 moles. I forgot to put moles, but that's what I mean right here. And then the original and the volume total, we have the original volume, we have the 1500 milliliters in meters cubed plus the meters cubed of the ones that we converted. We add those together and we get 1.6205 times 10 to the negative third meters cubed. I forgot to put meters cubed. Oh my gosh. All right, anyway. So then we use, of course, the ideal gas constant is 8.31 and the temperature is 77 degrees Kelvin. You plug it straight into the ideal gas law, isolating for pressure, and then we get that pressure is equal to about 15 atmospheres. And that's it. Thank you.